A disruption is the failure mode that keeps every tokamak engineer honest. In a fraction of a second, a confined plasma loses control, dumps its energy, and slams that load into the machine's own walls. If you want fusion to run for years, you cannot merely survive disruptions, you have to see them coming. Here is the physics. A tokamak holds 100 million degree plasma inside a magnetic cage. When the current profile, the density, or the plasma's shape drifts outside a stable window, the confinement can collapse. The plasma quenches, the current decays, and the magnetic energy has to go somewhere. Uncontrolled, that is the event we design against. But disruptions almost never arrive without warning. They announce themselves. Rotating magnetic islands, a mode locking in place, radiated power climbing, the plasma edge cooling. These are precursors, telltale patterns that show up milliseconds to tens of milliseconds before the crash. The problem is that no single sensor spells it out. The signature is spread across dozens of diagnostics, buried in noise, and it looks a little different every shot. This is exactly the kind of pattern a well-trained model is good at. It learns the shape of trouble from many examples, the abnormal signal that a human or a simple threshold would miss. So we frame it two ways at once. First, classification. Is this plasma heading toward a disruption, yes or no? Second, regression. If it is, how long do we have? The model outputs a time to disruption, a live countdown, updated every millisecond that turns a binary alarm into an actionable number. That countdown is what buys us room to act. The Kronos twin forecasts 50 to 100 milliseconds ahead. That does not sound like much, but in plasma control terms, it is an eternity. Enough time to back off the heating, adjust the coils, or fire a controlled shutdown before the plasma ever reaches the edge of stability. Now, a prediction you cannot trust is worse than no prediction because it makes you cry wolf. So every alarm is confidence gated. The model does not just say disruption, it says how sure it is. We act on the high confidence flags and hold on the marginal ones, so the system stays calm during normal operation and moves decisively only when the evidence is strong. There is an unavoidable trade-off underneath this, and we treat it openly. Set the trigger too eager, and you get false alarms that throw away good plasma. Set it too cautious, and you miss the real event. That trade-off is a curve, sensitivity against false positives, and we choose our operating point on it deliberately, tuned so that a missed disruption is far more expensive than a false one. When a high-confidence gated alarm does fire, the twin triggers mitigation, a pre-planned safe response. And here is the line we never blur. The machine learning model advises. A deterministic rules engine decides. The predictor can flag danger and recommend an action, but hard limits. Beta n at or below 5, Q 95 at or above 5. And the final trigger live in fixed, auditable logic, not in a neural network. The system also learns as it runs. Shot to shot, it updates on what it just saw, so it adapts to the specific machine rather than a textbook average. And when it raises a flag, it can show why, which signals drove the call, so an engineer can check the model's reasoning instead of trusting a black box. One honest caveat. Today, this is validated in open simulation against known disruption physics, not on an operating reactor. The real proof comes with real data at our first gate. But the architecture is built for that day. Predict early, gate on confidence, and let deterministic rules, not the model, hold the safety line. That is how you run a fusion machine for years, not seconds.